Welcome to section 6.4. This is really related to the last section, 6.3, where we talked about simple interest. Now we're going to talk about compound interest. So we first want to just talk about the way compound interest works and compare it to simple interest. And so I have this problem up here that will eventually start, but let's talk about some preliminaries. So with simple interest, let me get my pen working here. With simple interest, the interest is always based on the original principal, right? The original amount borrowed, the original principal. So if I borrowed, like in this problem above, if I borrow $1,000, then whatever the interest is on the $1,000 is what I'd pay at the end of year one. And I pay that same amount at the end of year two, and the same amount at the end of year three, and so forth and so on. So my interest is always the same and always based upon that initial amount either borrowed or invested. The difference with compound interest is the interest is computed periodically. So in compound interest, they compute the interest I'll say at regular intervals now. Okay, so that way you have some notes there. So compute that interest at regular intervals. And what happens is, let's suppose we start with $1,000. We apply the interest, which is based on the $1,000. Let's suppose that interest is something like 10%, something easy to work with. So 10% of 1,000 is 100. And so I would add $100 to that. And now at the end of the first year, I'd have $1,100. So then when I go the next year and I apply the interest is based on the new amount, 1,100. I said the next year, but I should say the next interval. And so we'll look at that as time goes on. But now instead of taking 10% of the original 1,000, I'm taking 10% of 1,100. And now I'm adding $110 as opposed to the $100 that I was adding before. So now I don't just get $1,200, I get $1,210. And the process continues and continues. With simple interest, it's always going to be $10, $10, $10. So let's see that kind of in action here with the first wording. So I'm going to go ahead and erase all this, and let me switch this from to a pixel eraser so it's a little bit faster. So we're going to come in here, and the reason why I'm erasing this is one, you could go back in the video, but two, I want to get up to this question that's up here. So let's look at this. Let's look at it from a 6.3 perspective and a 6.4 perspective. So I'm going to invest $1,000 at an annual interest rate of 4%. How much would I have at the end of 3 years if A, the investment paid simple interest? Okay, and we have a simple interest formula, right? But I don't want to go through that formula. I want to do exactly what I was doing before. So $1,000 is invested, and every year I'm going to add 4% each year. Well, 4% of 1,000, let's take 1,000 times 0.04, we get $40. So 1,000 times 0.04 is $40. So each year, I'm going to make $40 in interest. So here's my original $1,000. At the end of year one, so we'll put year one, I'll have $1,040. At the end of year two, I would take my 1,040 and add another 40. So I'm now up to 1,080. And at the end of year three, I'll take my 1,080 and add the same $40, and I'm going to get 1,120. Okay, at the end of year two. So, or at the end of year three, coming through there. apologize for the hesitation. I was looking at something at the same time. So 1,120. So B, if I have the investment, so this A was simple interest. And so B is compound interest. So if we do the same process, I'm going to start out in year one, and I have $1,000, but now I'm going to add 4% of that $1,000 at the end of year one because my interest is being compounded annually. That's important. That's why I'm just doing it once a year. So at the end of year one, the interest is going to be compounded. It's going to be the same 1,000 plus 40. So at the end of year one, I don't see a difference at all. It's 1,040. But when we get to year two, I'm going to take my 1,040, but now add 4% of the 1,040. So I got my 1,040, and instead of adding $40, if I take 1,040 times 0.04, I'm going to make $41.60. So at the end of year two, I have not just $1,080, I have 1,081.60. So I made an extra $1.60 in that process. Year three, I would take my 1,081.60 and add 4% of 1,081.60 and see what that is. So I take my 1,081.60 times 4%, and I get that I'm taking 1,081.60 and adding to it $43.26. So if I take my 1,081.60 and add $43.26, I get a whopping total of $1,124.86. So you can see that my amounts are different. In that 3-year process, because the interest was compounded, I made an extra $4.86 by doing nothing other than letting that interest be compounded. That's what compound interest does, is it keeps reapplying the percentage at different intervals at whatever stated. And so we had a nice formula to come up with this 1120 when we were in section 6.3. That was that the future value would be the principal plus the principal times rate times time. Or in our case, $1,000 plus 1,000 times 0.04 times 3. And when we run that in our calculator, we have 1,000 plus 1,000 times 0.04 times 3, and we get the 1120, right? That was the fastest way to get it, not stepping through each window of opportunity, because we wouldn't want to do that if they said, what do you have at the end of 25 years? Same thing here. There's got to be a formula for compound interest, otherwise it's going to get really cumbersome, because what if it was compounded quarterly? So I don't know if you're familiar with quarterly, but that means 4 times a year. Well, that kind of stinks because I'm going to have to do this reapplying every 4 times, and it's not going to be a true 4% each time because that's the annual interest rate. It's going to be 4% divided by 4, but I'm going to have to do that a whole bunch of times. So in this case, it was 3 years. I'd have to do it 12 different times. So luckily, there is a formula for compound interest. So the compound interest formula is what I want to show you next. And then we'll go through and look at some questions in the book and answer those. So I'll keep it the same as what they have in our book. This is the compound interest formula. That's general. Trying to apologize. I'm off scrolling to see what they have. And they have a good one. Sorry, they had multiple, but this is the one I would like to share with you. Awesome. So we have some familiar variables in there. A is what they use instead of future value, but it's the same thing as future value. A is the accumulated amount, same thing as future value. that they've been referring to. So there's no difference between A and future value. P is still the principal, the initial amount invested. So in the problem up here, P would be 1,000. The problem up here, R is the annual interest rate, still 0.04. T is the time, so T would be 3 as it matches that. And then there's this weird N thing. And I want to make sure you understand what N is. So N is the newest variable. So, and it's the only one that's new. N is the number of times the interest is compounded in a year. So that's what N is. The number of times interest is compounded in a year. So if you remember our previous problem, if we want to find the future value or the accumulated amount that would be present at the end of 3 years. If we invested $1,000, right, that's our P, times 1 plus R was 4%, and N was the number of times a year it's being compounded. Well, remember, we were being compounded annually, so that's 1 time a year. And N is 1, and T was 3 years. So I'm going to simplify this a little bit. A is equal to 1,000 times 1 plus 0.04 to the third power, right? So I'm just doing the division by 1 and the 1 times 3. So now let's plug that into our calculator. And we'd want to plug it in exactly how we see it. 1,000 times, open parenthesis, 1 plus 0.04, close parenthesis, raised to the third power. This symbol right here, this little triangle type symbol that doesn't have a base, is what's on my calculator for raised to a power. And so you want to find whatever button raises to a power. But we just type it in, 1,000 times, open parenthesis, 1 plus 0.04, close parenthesis, raised to the third power. And look what we get, 1124.864, 1124.86. We get the exact same value that we had up here, 1124.86, with minimal amount of work, right? Just understanding definitions. So let's talk about some common terms that they're going to use. This one was compounded annually. They'll use other words as well. Semi-annually is twice a year. So let me not put an equal sign there, and you'll see why in a minute. I'm going to put a colon. Semi-annually means that it's being compounded twice a year. You saw annually, I guess I should write that, and that's being compounded once a year. There's also quarterly that's very common, and that would be 4 times a year. There's also monthly, which you know is every month, so 12 times a year. And there's also daily, which you probably already know is 365 times a year. That's what's going to change in problems to problems. We still want to make sure that the time is in years, so time still needs to be in years. So I'll just highlight that again. If it's not, we got to adjust it for years. So if we take that same problem, I'm going to invest $1,000 at 4% annual percentage for 3 years. And this time, where interest is compounded. Now, before it was annually, and when it was annually, we ended up with $1,124.86. Let's compound it monthly, just to play around with and see the difference. Okay, so what would change? Let me get our formula out here so you don't have to go back in the video. Obviously, this is something you want in your notes, to have that in your notes. So A is equal to 1,000 is what we're investing. 1 plus 0.04 is the interest rate. The number of times it's going to be compounded a year. If it's done monthly, then actually let me highlight that. If it's done monthly, then we should have a 12 under here, just to make use of the different colored pens. So, and then the monthly produces a 12 up here times 3. Now, I want this to make sense to you. Why the 12 is each time that interest is applied, it's 1/12 of the annual interest, so that it builds up to be the full 4% interest. You're not going to get 4% every month, but you're going to get a 12th of 4 every month. Okay? And then that's going to happen a total of 12 times 3 times. Now, something I recommend, I don't recommend you doing too much. So I'm going to leave in black everything that I'm not changing from what's above. That's up to here, but I highly, highly recommend that you do this product up here so that it's a single number. 12 times 3, I'll put it in red, is 36, right? So on your calculator, you'll do 12 times 3. Now we're in a very good position to put this in our calculator, and it should feel just like the last one. So in my calculator, I would put 1,000 times, open parenthesis, 1 plus 0.04. And remember, fractions are division, so divided by 12, close that parenthesis, and raise it to the 36th power. So I'm going to plug that in now. 1,000 times, open parenthesis, 1 plus 0.04 divided by 12, close parenthesis, and raise that to the 36th power. And look what I get. $1,127.27 if I round. There's a 1 that comes after that, like you'll see. So look how much more money I got. Not drastically more. Simple interest was $1,120. Compounding it annually gave us an extra $4.86 for $1,124.86. And compounding it monthly increased that by $3 about to $1,127.27. So pretty cool. That's how it works. So the homework is designed for you to get to play around with that. And so as you go into the homework, the first problems assigned starts with number 9, and they do exactly this. So I'm looking at those problems, and all the time that they're asking you to calculate it on is given in years. That's good. I'm going to just choose one at random. So actually, I'm going to choose one at the bottom. So this is number 16. Here's what they have. They have principal is $9,450. The annual interest rate, the annual percentage rate is 3.99%, and it's compounded daily. For 25 years. So if you had something that could last 25 years and you dropped $9,450 in it, paid 3.99% annual interest rate compounded daily, what would you have at the end of that is our idea, is our question. So we know the formula. And so I'm going to just take a moment to highlight different things. We'll have a principal that plays its role. We'll have an interest rate that plays its role. And we'll have a compounding time that plays its role. And we'll have, just seeing what colors, a year that plays its role. And then we just go in and everybody play their role. So using the same colors, my principal is $9,450. 1 plus is set and stagnant. You're not ever replacing that. R, the rate was in red. So that is, remember to, I know you're good at this, but I just want to stress it, to move it 2 decimal places back. And then I need to know N. For daily, that is 365 times a year. I'm trying to be good here, so that's the same 365. and that's multiplied by 25. So there it is, all color-coded, if that helps. So A is equal to 9,450 times 1 plus 0.0399 divided by 365. Don't figure that out on your own and rewrite it. That's crazy. But do rewrite that product. Find out what 365 times 25 is. $9,125. Oh, not dollars. 9,125 times. That's how many times it's going to be compounded in a 25-year process where it's happening every day. So you just learned that there's 9,125 days in 25 years. All right, now we just plug it into our calculator. So we're going to take our 9,450, multiply by open parenthesis, 1 plus 0.0399 divided by 365, close that parenthesis, and raise to 9,125. And we get a number. And the number we get is a big amount, $25,622.23. That is the answer to our question there. That's how much money you would have if you had interest compounding daily for 25 years under these parameters. And that's what you're doing for problems 9 through 16, as well as some of the ones at the end. If you look at your homework assignment, there's problems thrown in like 35, 37, 39, and 41. They're just verbal descriptions of these types of questions where you just find the information within the paragraph that's there. Then they ask another question, which is very important. They asked for us to find the present value for a desired future value. So honestly, it's going to be a manipulation of this equation. This is the one for the future value, right? And you're going to be solving for p. So you don't have to go through all that algebra. They give us a formula, and I would encourage you to write it down. So the present value formula that they give, it looks crazy, but you can do it, is the idea. And I'll try to walk you through how to plug it into your calculator. So when they ask for the present value, you want to take what you want in the end, which is the accumulated amount or future value, 1 plus r over n to the n times t. Okay, is how they have it written. Okay, I'm going to rewrite that a little bit differently, a way I like. I would write it as n times t, just like that. Yeah, that is just a manipulation of what you see there. You can see that this guy right here just got shoved right underneath that guy. But when you remember what's happening when you solve for present value, you're saying, what do I have to put away today to ensure that I have this much money later on? An excellent question, right? How much can I save in today's money to have an experience with, or to accumulate an amount that I'm going to need in retirement or whatever? So let's look at something like number 22. Number 22, and others like it, 17 to 24, 22 just somewhere in there. The question is, compute the present value. So that's how you're going to know that you want to do present value, and you're going to go to that one. If you want a future value and you know somehow that the annual percentage rate is going to be 4.23%, compounded monthly, which is common, for 35 years. You want to know, how much money do I have to put away today in present day time in order for it to grow to $800,000 if I'm planning on about a 4.23% interest rate over the next 35 years. And so that's probably based upon a lot of projections and historical analysis. But we can run the numbers and see. So we have the formula, right? It's right up there, but I'll rewrite it here. Present value is what they're asking for, so we're going to go to that formula. And it's the accumulated amount, what you want in the end, times 1 plus r over n, divided by 1 plus r over n to the n times t. And let's go put in the values again, much like we did before. So we're looking for the present value, what we want it to grow to, what we want its future value to be, what we want its accumulated amount to be is 800,000. And that is all over 1 plus, and they must have given us an interest rate. They did, 4.23%. So we're good now. We know to put that in as 0.0423. And then it's compounded monthly, so we're going to use our 12 again. And that's to the 12 times 35. So remember my suggestion. And the suggestion is just so it's easier to plug into your calculator. Present value is 800,000 divided by 1 plus 0.0423 divided by 12. None of that's changed. I'll highlight what's changing to the 12 times 35. That's what I'm going to figure out. 12 times 35 is 420. So just to highlight in red. I also wanted to make sure you see this is extended, like everything's under that bracket. So let's be careful. Here's how we plug this into our calculator. Whoops, sorry about that. We take 800,000. I'm going to go over here. Let me do some erasing here. And I'll go way off to the side. We're going to take our 800,000 on our calculator. We're going to type in divide by, open parentheses, 1 plus 0.0423 divided by 12, close those parentheses, and raise to the 420. So it's a very similar process. Your calculator will know to do the work in the parentheses first, then the power second, then this division last, the division that's between the 800,000. So let's plug it in. We should be expecting a number less than 800,000. So I almost plugged in 80,000. So just make sure you have the right amount of zeros, divided by 1 plus 0.0423 divided by 12, close those parentheses, and raise to the 420 power. And we get that in order to have my money grow to 800,000 in 35 years under the parameters that were given, I need to invest right now $182,493.58. That is what's going to allow me to have my money grow to 800,000 in 35 years if I'm expecting a 4.23% annual rate that's compounded monthly. And that's what you're doing. You're basically, these sections are nicer, I think, than the 6.2 section because you have these set formulas that you're going through and looking at. So far, the formulas are this, that the accumulated amount in a compound interest is very nicely given as P times 1 plus R over N to the NT. And if they ask for the present value, then that's that accumulated amount, all divided by 1 plus R over N to the NT. And those are the two so far. There is a third one that they ask about, and it's questions 25 through 30. And they want to talk to you about the effective annual yield. So let's go back to some questions that I did before. So I'm just going to scroll up here. And remember, we got different amounts when the interest was simple interest. Compounded annually was that. Compounded monthly was even more, right? $1,127. And if I would do daily, it'd be even more. Interestingly enough, there's a tipping point. We don't need to talk about that where it doesn't increase without bound. There is a bound for this. It will get less and less and less of money you're adding in. So that's why people typically do a daily type of thing like here. But we get more and more interest as it's compounded. What we want to do is figure out what is the effective yield. And so the effective yield is like the true annual percentage rate that's going on. And so they'll talk about effective yield in the book, and they'll give you a formula for it. So all you have to do again is apply the formula. So effective yield allows us to do direct comparisons between simple interest and compound interest by converting the compound interest to its equivalent simple interest rate. So that's what we're doing. The effective yield takes the compound interest and converts it to its effective simple interest rate over a year. And there's a formula to do that. The effective annual yield has a symbol y. And so y is equal to 1 plus r over n to the n minus 1. That's the formula that we're going to use whenever they ask us an effective yield problem. So, for example, if you remember, let me get some values out here. When we invested $1,000 and the interest was compounded annually. Well, actually, let me not do that. I think that would be too much back and forth. Let's go look at a problem that we can investigate. Let's look at a previous problem. Let's look at this one right here, where we took our 9,450 and raised it to 25,622.23 by compounding interest daily. So realize it doesn't need everything in there. This formula says what I'm going to need is, I don't care about what you initially invested. That won't make a difference. That's just going to be your growth or your basis for growth. What I do care about is what interest you were paying. And so as I come back up here, in this problem, we were getting an annual interest rate of 3.99%. And so we put our 0.0399 in there. The compounding for this one up here was daily, so our n is still 365. And notice there's not a time in there. So I put the same 365 there minus 1. So let's look at that. So we take our 1, and we just plug it in exactly how we see it. Open parentheses, 1 plus 0.0399 divided by 365, close it, raise it to the 365, and subtract 1. So 1 minus 0.0399 divided by 365, close parentheses, raise to the 365 power, and subtract 1. And here's what I get. I think I plugged something in incorrectly. I'm going to go ahead and replug this in. Sorry about that. And you could just plug it in as one big string. And yeah, I had hit something. I think I hit 1 minus because I got a negative number out of it. So I just plugged it in and hit equals the same way that's there. And I got 0.040704,429. So the effective the effective yield is 4.07%. So interesting, right? It was 3.99, but I'm really getting 4.07% every year if it was converted over to simple interest. And so you're going to have problems just like that. So let me go grab one more from the last section. And that is, I'll just grab number 28. Number 28 says, find the effective yield. And what's nice is it just gives us the information we need. Where you have an annual interest rate of, in 28, it's 2.56%. And it's compounded quarterly. Good, we haven't seen that yet. So our effective yield, we just use our formula. Remember, it was 1 plus r over n to the n minus 1, right? 1 plus r over n to the n minus 1. Cool. Well, we have everything we need. 1 plus r 0.0256 all over n, compounded quarterly. Do you remember what that is? It's 4 to the 4th minus 1. And so what's the effective yield? It is 1 plus 0.0256 divided by 4. Raise that to the 4th power and subtract 1. And I'm getting 0.0258681. So if I'm looking at this as a percentage, it is 2.59% if I keep the same rounding. So you get a little bit extra yield in there, but that's what we know is happening. The compounding causes us our money to grow a little bit more. And this is just giving us a picture of that. So this is what's called the effective yield. It's the last group of problems. Remember, you'll also find the future value as well as the present value in here. So hopefully this video does a good job of guiding you through the homework. It does give examples of every one. So thanks for watching.